Okay guys, in this next video we're going to cover this section on the evolution of atomic theory. And so we'll outline a few of the experiments involving the development of modern atomic theory, and we'll show you the, at least in outline form, the results of these famous experiments. And then we'll talk about the subatomic particles that make up every type of atom. And then we'll have a bit of discussion on isotopes. So in this first experiment, we're talking about the cathode ray experiments conducted by J.J. Thomson, which allowed him to discover the electron and determine the charge to mass ratio of the electron. So this device here is called a cathode ray tube. Inside the cathode ray tube, you have a couple of electrodes. You have a cathode from which electrons, a beam of electrons, stream out, and they pass by a hole in this anode. And then the electron beam makes its way down to the end of the chamber here. And you can deflect this beam of electrons using either electric plates or by using a magnet. Okay, and so at first, J.J. Thomson didn't know exactly what he was seeing. They were called cathode rays. But by analyzing the results of this experiment, J.J. Thomson was able to conclude that the particles in the cathode rays were negatively charged, and by deflecting the beam in a very careful way with the magnetic field, he was able to deduce from the deflection the ratio of this particle's charge to its mass. And so that's what we mean by the charge to mass ratio. So J.J. Thomson is credited with discovering the electron and measuring its charge to mass ratio. In a second experiment, this time performed by Robert Millikan, this oil drop experiment, as it's called, Millikan was able to determine the mass and the charge of the electron. And so here's how that works. You take oil, so oil droplets that are atomized, meaning they're produced in a fine mist, and they're injected into this chamber. Okay, and you can charge the droplets. That is, you can add charges to the droplets, either by irradiating them or through just frictional processes. The droplets will pick up a charge. And some of the droplets will pass through this hole in this positively charged electric plate. And just due to the force of gravity, they will start to fall down. And what Millikan did was he was able to tune the voltage between these two electric plates in order to suspend the droplet in front of this eyepiece, so he could observe the droplets. And what he did was he found the voltage required to make particular droplets be suspended. That is, they stop falling. And so if the droplets are charged, if you apply a voltage across these plates, you can get the droplet to stay put long enough for you to observe it. And so by back calculating the voltage required to suspend the droplets, he was able to determine the charge on different droplets. And so this would be a typical result. That is, after measuring the voltage required to suspend 5 droplets, he would get these types of charges coming out of his calculations. And what you'll notice is that the different charges that you see are all multiples of this lowest charge, this 1.6 times 10 to the minus 19 coulombs. And so the idea here is that these oil droplets, they pick up electrons. Sometimes they pick up 1 electron, sometimes they pick up 2, sometimes 3 or 4. In any case, they pick up a number of electrons, and then you can figure out by looking at the data, the lowest charge that you see in your calculations would indicate the charge of just having a single electron on the oil droplet, and all other charges that you get would be multiples of that. That is multiple electrons. So Millikan was able to determine the charge of the electron using this experiment, and then by combining that with J.J. Thomson's charge to mass ratio, you could then calculate the mass of the electron. And so what's known is that the electron has a very small negative charge, so small on the SI unit system, and it also has a very, very small mass. So the electrons are particles that are smaller than atoms, and they appear to be common to different substances. In this next experiment, we're talking about the Rutherford gold foil scattering experiment. Rutherford studied radiation, so different radiation sources, and in this experiment he took a sample of radium, which produces alpha particles, and he shot these alpha particles towards a very thin gold foil. And in most cases, the alpha particles just pass straight through the gold foil. In some cases, you get small angle deflections of the alpha particles, which strike the detector at these angles here. But every once in a while, he would get an alpha particle, a high energy alpha particle, being deflected straight back at him. And this was rather surprising because the alpha particles have such a large momentum that they should really just go straight through this foil. But every once in a while, you get one of them coming back. And so what Rutherford proposed was that the atoms of gold were made up of some type of positively charged nucleus, which was capable of deflecting the alpha particles, and that the atoms were mostly empty space. So the idea here is that you have a nuclear core of these different atoms, but the atoms themselves, with the electrons somehow moving around them, are generally empty space, which is why most of the alpha particles just go straight through the foil. Every once in a while, an alpha particle gets close to a nucleus, and so it scatters off with some small deflection angle. But rarely you will get an alpha particle directly striking a nucleus and then bouncing completely backwards. And so that's the new result from Rutherford's experiment. He basically discovered the nucleus of the atom through this type of experiment. So that leads us to the nuclear model of the atom. This is the modern day understanding of matter. At the center of each atom is a nucleus. It's a very dense, positively charged core. It consists of protons, which are positively charged, and also neutrons, which are particles that have no charge. And then the electrons are negatively charged particles. They have very small masses, and they orbit around the nucleus of the atoms. And to give you a sense of the scale of things, atoms are typically about an angstrom, so 10 to the minus 10 meters. The nucleus is 5 orders of magnitude smaller. It's about a femtometer, 10 to the minus 15 meters. To put that into context, if the nucleus of an atom were a blueberry, then the size of the atom would be roughly equal to a football stadium with the nucleus at the center, and the electrons would orbit around the nucleus. And so, generally speaking, an atom consists of mostly empty space. All of the mass of the atom is in the nucleus, and then the size of the atom is essentially due to the electrons, which are orbiting around. This table here lists the charge and the mass for different subatomic particles. Electrons have a negative charge, protons have a positive charge. We use a different unit scale for electrons and protons. We use this unit charge scale, and so what you need to remember is that electrons have a unit charge of -1, protons have a unit charge of +1, and then if you wanted to evaluate that charge on the SI unit system, you would use this conversion factor here. So 1 electron has a charge of negative 1.602 times 10 to the minus 19 coulombs. Here we have the masses using grams, and so protons and neutrons have about the same mass, but you see that the electron mass is several orders of magnitude smaller. And so you want to understand that electrons are very light compared to protons and neutrons, and that protons and neutrons have about the same mass. If you like, you can think of using a different unit system. So this would be the unified atomic mass, where the mass of a proton is about 1, the mass of a neutron is about 1, it's a little bit heavier than the proton, and then the mass of the electron is quite a bit smaller than the proton mass. We'll go ahead and talk about this next section as well. So looking at atomic structures and atomic symbols, we want to be able to write and interpret nuclide symbols that depict atomic number, mass number, and atom charge. We also will talk about atomic masses and isotopes in this section. So atoms are represented by different atomic symbols, which usually consist of either one letter or two letters. The first letter is always capitalized. The thing to note about atoms of a given element is that they all have the same number of protons. So what defines the atom's identity, what makes an atom an atom of that particular element, is the number of protons in the atom. And we call this the atomic number, and it usually has the symbol capital Z. So Z represents the number of protons in the nucleus of a particular element's atom. Neutral atoms would have an equal number of protons and electrons, right? If each proton has a +1 charge and each electron has a -1 charge, then in order for the atom to be neutral, you would have to have equal numbers of protons and electrons. If you're talking about if you don't have an equal number of protons and electrons, you will have what is called an ion. Okay, and so an ion is an atom that has an electric charge. It has an electric charge because it has an unequal number of electrons and protons. And you can calculate the ion charge by taking the atomic number for that atom and subtracting off the number of electrons in the ion. Sometimes you get a positive number, sometimes you get a negative number. Let's talk about isotopes next. So the same atom can have different numbers of neutrons, as it turns out, and so in the nucleus. And so what we call the mass number is the sum of the number of protons and neutrons in a given nucleus. And we call atoms that have the same atomic number but different mass numbers, that is, they have different numbers of neutrons, we call those isotopes. Okay, so there are different isotopes of a given element. Each isotope has the same atomic number, but will have a different mass number due to the different number of neutrons in the nucleus. The term nuclide refers to a nucleus with a specific value of Z and a specific value of A, the mass number. And nuclide symbols can be represented in words, where you use the name of the atom followed by the number, the mass number A, or you can use this symbol form here, where you would use the atomic symbol. In the lower left-hand corner, you put the atomic number. In the upper left-hand corner, you put the atomic number. And if the atom is charged, that is, if you have an ion, you could also put the charge on the ion in the upper right-hand corner. So what we need to be able to do is interpret nuclide symbols, both the word form and the symbol form. So we're going to go ahead and turn to this problem here, where we are being asked to write out the nuclide symbol for a nucleus with 38 protons and 50 neutrons. And what we'll need in order to do that is the periodic table. So I'm going to pull up my periodic table real quick, and I'm going to place it right here for us to work with. So we want to find the nuclide symbol that has 38 protons and 50 neutrons. Remember that our nuclide symbols have the letter symbol for that atom. In the lower left-hand corner, you have the atomic number, which is the number of protons. In the upper left-hand corner, you have the mass number, which is the number of protons plus neutrons, and then you may or may not have a charge, depending on whether you're talking about an ion or not. Okay, so we have a nuclide that has the number of protons is equal to 38, and the number of neutrons is equal to 50. Right? The number of protons is equivalent to the atomic number, and the mass number is equal to the number of protons plus the number of neutrons. Okay, so that would be 88 in this case. Okay, you look to your periodic table, and what it shows you are the atoms listed in increasing order of atomic number. So hydrogen has an atomic number of 1, helium has an atomic number of 2, lithium has an atomic number of 3, and so on. So we want to find the atom that has 38 protons. In this case, it's strontium, and the symbol is Sr. We would put the atomic number in the lower left. We would put the mass number in the upper left. We'll just assume that this is a neutral strontium, and so we'll just leave it like this. If you were to write out the name, you would say strontium 88. So that's the name of this nuclide. For the next one, we have a nucleus that has 17 protons. So the number of protons in the atomic number is equal to 17. The number of neutrons is equal to 18. So the mass number, which is the sum of the two, let's see if I can do the arithmetic, 15, so that'd be 35. Okay, you look to your periodic table. Atomic number 17 is chlorine. 17 goes down in the lower left, and the mass number 35 goes in the upper left, and we would call this chlorine 35. Let's see. I did want to do this last one as well. Or we have two more. So we've got iodine atoms, and in this case we are considering an iodine that has a charge of -1, and we're being asked to determine the number of protons, the neutrons, and electrons for these iodine atoms. So we will start with the mass number, A, equals 127. We know it's iodine, and so we can look up on the periodic table, we can look up iodine, and we find that Z equals 53, which means that, the number of protons is equal to 53. The number of neutrons will be the mass number minus the atomic number. Okay, so we'll have 127 minus 53, so that's giving me 4, so we would have 74 there. And then finally, since we know that the charge is -1, and that the charge is going to be the atomic number minus the number of electrons, we would get from this that the number of electrons is going to be 1 greater than the atomic number. The number of electrons is going to be 54 in this case. Okay, so we've determined the number of protons, the number of neutrons, and the number of electrons for the iodide ion. In this last example here, part D, we're being asked to do the same thing for these platinum ions, possibly. So we have a mass number of 195. We know that the number of electrons is 74. And looking at our periodic table, platinum, if we find platinum right down here, that's atomic number, which equals the number of protons, 78. The number of neutrons will be the mass number minus the number of protons. So 195 minus 78. And I don't want to get it wrong, so I'll just use my calculator real quick. I'm getting 117 for the number of neutrons. What else did they want us to do here for platinum? What is its charge? Okay, so the charge will be the atomic number, the number of protons, minus the number of electrons. Okay, so in this case we've got 78 minus 74, so we are going to wind up with a +4 for the charge on the platinum. And so we could write that as platinum. We put 78 down here, 117 goes up there, and then we would put the charge as 4+ for this particular ion. Okay? So you want to be able to solve this type of problem. You need to be able to interpret nuclide symbols. You need to be able to calculate numbers of protons, numbers of neutrons, numbers of electrons, given the periodic table and information like we see in this problem. Let's talk about atomic mass next. So different atoms have different masses, and in working with atoms, we typically do not use kilograms to represent atomic masses. It's just not a very convenient unit to work with. Instead, we use atomic mass units. And atomic mass units are based upon the carbon-12 isotope. The AMU is defined as 1/12 the mass of a carbon-12 isotope. Carbon has an atomic number of 6. Carbon-12 with a mass number of 12 has 6 protons and 6 neutrons. We know that protons and neutrons have roughly the same mass. So if we take the mass of a carbon-12 isotope and divide it by 12, that gives us what we call the AMU, which is roughly equal to the mass of a proton or a neutron. Not quite, though. And then here is the conversion factor between AMUs and kilograms. So 1 AMU is about 1.67, or 1.7 times 10 to the minus 27 kilograms. The atomic mass for a given element is a weighted sum over all of the naturally occurring isotopes for that particular element. So we've learned what isotopes are. The next thing to know is that certain isotopes for a given element are stable in nature, and other isotopes are not. Okay? So in nature, you'll find that there are certain isotopes for different elements, and the atomic mass that we use is a weighted average over all of the naturally occurring isotopes for that particular element. For example, sodium-23 has only one naturally occurring isotope, and so the atomic mass of sodium is really just the mass of a sodium-23 isotope. However, a different element like oxygen is known to have 3 naturally occurring isotopes: oxygen-16, oxygen-17, and oxygen-18. All of these isotopes can be found in nature. Most of the oxygen isotopes are oxygen-16, so 99.759% of oxygen atoms are oxygen-16. A much smaller fraction are oxygen-17, and a fairly small fraction are oxygen 18. The atomic mass of oxygen, which is listed on the periodic table, is a weighted average of the isotope masses for all of the naturally occurring isotopes. How do you calculate a weighted average? You take the mass for each isotope, you multiply by its fractional abundance, and then you add that up over all of the different isotopes. That's what this symbol sigma here means. It means to add up. So for each isotope I, you multiply the abundance times the isotope mass, and then you add that up over all of the different isotopes that you have. And that gives you the weighted average. Both the isotope masses and the fractional abundance for a given isotope can be measured using mass spectrometry. In mass spectrometry, you have a sample of vapor, elemental vapor, I should say atomic vapor, that is charged using an electron beam. Okay, so you have the atoms flowing in this way, you have electrons coming in here, the atoms become charged, and then they can be accelerated through these electric plates, and then they encounter a magnetic field which causes them to turn, and the amount that a given isotope will turn depends upon its mass. And so lighter isotopes will be deflected more than heavier isotopes. And so by counting the number of times a given isotope hits the detector, you can evaluate both the abundance of that isotope and the mass of that particular isotope. So here's some sample data for zirconium. Zirconium isotopes come in 90, 91, 92, 93, and 96 flavors. And you can see here that most of the zirconium atoms, about 50% of them, are zirconium-90, but there's a good fraction that are 91, 92, and 93, and a smaller fraction that are 96. So both the abundance and the isotope masses can be measured. And then what we need to be able to do are problems like this, where you are expected to take this data and to calculate the average atomic mass for a given element. I'm actually going to skip this one. That is, I'm not going to go through the details because it's a little boring. But here's how you solve this problem. What you need to do is to take the isotope masses here, listed in AMUs, and multiply them by these fractional abundances. So these aren't the percentages. These are the percentages expressed as a fraction. So for example, chromium here, chromium-52, 83.79% of all chromium atoms are chromium-52. So the percentage here is expressed in terms of a fraction. So you take the masses times the fractions, and then you add those up. So you might make a third column where you take this number times that number for each of the rows, and then you add up that third column to give you the average atomic mass. I'm going to work it out explicitly for this shorter problem here, where we're doing the exact same thing, but for chlorine. So I'm just going to hide my periodic table there. Okay, so in this problem, we want to determine the average atomic mass of chlorine. So what I'm going to do is I'm going to take this column of numbers times that column of numbers, and I'm going to make a third column just right here. So I'll take the 34.96885 and multiply that by the abundance of chlorine 35. I'm going to go ahead and write down that number, 26.49624 and some change. And I want to take a quick look here at the sig figs. You'll notice that this number has 1, 2, 3, 4, 5 sig figs. This one has more. We're multiplying here, so this number should only have 5 sig figs. 1, 2, 3, 4, 5. That's the last significant figure there. I'll do the same thing for the next row, 36.9659 times 0.24229, and that's giving me 8.9 956, 4, 6, and some change. And again, we should have, it looks like 5 significant figures. So 1, 2, 3, 4, 5. The last significant digit is that one. And now I'm going to add this number in my calculator to the one above, plus 26.49624. And so I get 35.4527079 and some change. And we want to evaluate now, since we're adding, we want to evaluate the last significant decimal place. So we have, looks like 3 decimal places here, 4 decimal places there, so we're going to keep our last sig fig at the 3rd decimal place. So we're going to round up 35.453 AMUs is the average atomic mass of chlorine. And this is a weighted average of both the chlorine-35 and the chlorine-37 isotopes. In this next problem, this one's kind of challenging actually. So this one involves a bit of algebra. And I'll at least set it up for you. But I might save the details of the calculations for you, the numerical work for you. But I do want to talk about this problem. So copper consists of copper-63 and copper-65, and we see that the atomic masses of each isotope were given to us. They also tell us the average mass of copper, and then they ask us to find what is the percent composition of copper in terms of these two isotopes. So what they're asking you to calculate are the fractional abundances of the two isotopes. And so here's how you work out that problem. So first of all, the average mass of copper, which I'll write like that, is going to be a sum of 2 terms. It's going to be the mass of copper-63 times the fractional abundance of copper-63 plus the mass of copper-65 times the fractional abundance of copper-65. So we know this number, and we know the 2 masses, and we're being asked to solve for the fractional abundances. Notice that we have 2 unknowns, but only 1 equation. And you may remember from algebra that that's an unsolvable situation. However, there is a second equation that we can use. We can use the fact that the fractional abundances of the 2 isotopes need to add up to 1. Right? So 1 will equal F63 plus F65. This is true of all, kind of fractional compositions. Okay? So in this case, we have a second equation. So now we have 2 equations and 2 unknowns. You need to substitute this equation into that equation for one of these 2 variables, and then find the other, and then you can back substitute into this equation to get the other unknown. So I'm going to leave that as an algebra exercise for you guys, and I'm going to go ahead and stop the video here, and we'll pick up with chemical formulas in the next one.